To Proportion Z Inference, the parameter that we're going to be looking at is the difference of two population proportions, so our statistic will be the difference of two sample proportions. Recall the standard deviation formula for one sample proportion and its distribution right there. If we square it to get variance, it looks like this. Now, any time that we're taking the difference of two things, like the difference of two sample proportions, it is a joint distribution. And so we can't add standard deviations together to get the new standard deviation in a joint distribution, but you can add variances together to get the new variance. That is why, when you see this formula, we're taking the variance of each, adding them together, and then we're taking the square root to get the standard deviation of this joint distribution. Now, I try to inject a little bit of humor in a lot of these videos just to make it palatable. This next one may offend you, and I apologize ahead of time. But suppose an experiment was conducted on students with multiple personalities. You're right. That is offensive. I can't believe you said that. Yeah, it's terrible. Shut up and let the man talk. Anyway, just a joke. This is really actors. They're student actors. They're in a small drama club, so they have to play various roles, okay? Hence the idea of multiple personalities. So we have that. Okay, now, some actors are randomly receiving drug A and some drug B. And really, it's not drugs at all. These are vegetables, and this is Hostess Twinkies. So even though in the world of statistics we talk about things like joint distributions, even this is just vegetables, this is just Hostess Twinkies, it's all just in good fun. So we look at what happens after 2 weeks of rehearsal on either the vegetables or the Hostess Twinkies, what proportion in each group is able to recite all of their lines flawlessly. So that's what we're going to examine. All right, we're doing a 90% confidence interval 4, and again, the confidence intervals that you're asked to construct, in the prepositional phrase, they're going to tell you what the parameter is. It's the difference in proportion of students with multiple personalities who are able to recite lines flawlessly on drug A versus drug B. Huh, how ironic. I misspelled flawless. And so what happens is we have this down here. If there's a 90% confidence interval on the difference of proportions, this is a joint distribution. We're looking at trapping the middle 90% and therefore 5% on each tail. So the margin of error is going to involve a z-score of 1.645. We can go 1.645 standard deviations in each direction and expect to trap the middle 90% of all the differences in these proportions. So we go to our formula sheet and we know that in any confidence interval, we're going to take our statistic plus or minus critical value times standard deviation of the statistic. Since we know our parameter is the difference of two population proportions, we're going to use the difference of two sample proportions, add and subtract the critical z-score times, there it is again, the sum of the variances, taking the square root of that. So if we were to go to our calculator and let it calculate some of the information for us, we would go to the two proportion Z interval and we would enter the data that we have. So we're told, let's suppose, that we took a sample of 81 students and they received the vegetables, and we had 66 of them 2 weeks later reciting their lines flawlessly. And then we had 60 out of 78 of the students who were given the Hostess Twinkies, that's a T, recite their lines flawlessly at the end of 2 weeks. So we put that information into the two proportion Z, run a 90% confidence interval, and then we can record the results that we got. It will give us the P1 hat, the P2 hat. Just make sure to write all those things where they belong in the confidence interval formula. The result we get is from negative 0.06 to about 0.15. So we want to be able to interpret that interval accurately. So remember what our parameter is. The parameter is the difference of the students who can recite their lines flawlessly, whether they, the difference between those getting vegetables, those getting Twinkies. So because this is a negative over here, we say that we're 90% confident that the difference in the proportion of students who could recite their lines flawlessly 2 weeks later is somewhere between 6% more of the students with Hostess Twinkies able to recite their lines flawlessly, up to and including 15% more of the students receiving vegetables reciting their lines flawlessly. So it's important for us to remember what the parameter is that we're estimating, and we need to discuss what's up with the negative and the positive. Now from there, we might go to a hypothesis test. So somebody might claim that the proportion of flawless actors taking vegetables is greater than the proportion of flawless actors taking Hostess Twinkies. So here's our alternative, and here's our null. Now we have a bit of a dilemma. What do we put in the as the mean of this sampling distribution? Well, it's a good question. What we need to realize is if the null is true, we say that the two proportions are equal, and if that's the case, the difference of the proportions must be 0. So once again, that's our parameter. The parameter is the difference of two population proportions. We're assuming it's 0, there is no difference. So 0 is what we put in the mean of this sampling distribution with all the theoretical differences in the two sample proportions. But the nerd's asking a good question. So wait a minute, what about the standard deviation of this joint distribution? How do we go about calculating that? Because the problem doesn't tell us how big these proportions are. It just says test to see if they're the same or if one is greater than the other one. So this is where the pooled p hat comes in, and it's nice if we can understand the idea behind all this. Recall that in a one proportion z test, the null would be that p is equal to 0.7, and there is the alternative. So that means if we're coming up with the sampling, the standard deviation of this sampling distribution for proportions, we would assume the null is true, and we would use the 0.7 and then the failure rate of 1 minus 0.7 in our formula for the proportions. In any joint distribution, you'll have one population proportion, another population proportion. You're going to add their variances together and take the square root to get the joint distribution standard deviation. Well, the dilemma is, in our test, all we know is that we're assuming that the two proportions are equal, but we don't have any indication of what those same proportions would be so that we can use them in our standard deviation formula. And so this is why we have to pool the p hats together, because we need to estimate the same population proportions that are assumed in the null. So we're assuming that these guys are the same, but we need to estimate what that same value is, because we need to put that value into our standard deviation formula. So the way we pool the p hat is literally to assume that both samples came from almost like the same population, because we're assuming the population proportions are equal. So we pool them to estimate what that same proportion would be for these two guys in the null so that we can use it in our formula. And by the way, if that's the only understanding you come out with, that's fine. One of the reasons we don't just average the two sample proportions together is that theoretically, the bigger of the two sample sizes would tend to be the more accurate one. We want it to carry more weight. That's why we don't just average the two sample proportions together, but instead we pool them so that this sample size, this sample would carry a little bit more weight than the other one. If you understand that, fine. If you don't, it's probably not the end of the world. So what we do is if we run our test on the calculator, then we can type in the numbers that we need to be able to show our work successfully. And so we're going to put in again all the statistics we got, the successes and all. We're going to say that P1 is greater than P2, and we're going to calculate this. And so what we end up with is these results right here. There's our z-score of 0.709. So we can put in the work to show our z-score. This is our statistic minus our parameter. We assume that the null is true, that there's no difference in the proportions. So we subtract these puppies right here. See that our pooled p-hat, and the calculator gives it to you, the pooled p-hat, that will go as the assumed proportion for both of the populations. I know that AP in its formula sheet has us factor those out. I'm not a big believer as a math teacher of memorizing extra formulas when they're really the same as the previous formula. So I hope there's no problem there. But at any rate, that's the work shown. There's the z-score, there's the p-value. Because the probability of a type 1 error is greater than 5%, we fail to reject the null, so the evidence fails to suggest that the proportion of students reciting using vegetables is any greater than the flawless reciting of the students receiving the Twinkies. The assumptions or conditions that have to be met for us to be able to do two-sample inference on proportions: the data has to come from a random sample. The two samples need to be independent of each other. Actually, probably should be saying mutually exclusive of each other. Normality. Before we said that the success rate, NP, would have to be at least 10. We can cut it in half because we're dealing with a two-proportion situation, the difference of proportions. So we can say the number of successes and failures would be at least 5 in both cases. And then to make sure that we can trust our variance, we should reference the fact that the populations we're sampling from would be very large, at least 10 times as big as the two sample sizes that we have. So follow the formula sheet, know your parameters, know your statistics. And one of the toughest ideas, I think, in all the of all this curriculum is, why do we pool the p-hats? When do we pool the p-hats? And it's in the two proportion Z tests that we run comparing two proportions. So good luck.